In this video, we're going to apply the conservation of momentum to a differential fluid element. So let's start with the concept. The conservation of momentum says that the rate of increase of momentum in a system has to equal the net rate of flow into the system plus the net external forces acting on the contents of the system. In other words, this is really just F equals ma, but for an open system, where the left-hand side is ma, the right-hand side is flow of momentum in and out plus the forces acting on it. Okay, so let's get back to our differential cube. I realize there's a lot to stare at here. We'll work through it very slow. We've got a box. The box has dimensions of dx by dz, and it's dy tall. We're going to call the zero coordinate back here, and so this is location x, which makes the right-hand side of the box x plus dx. The bottom of the box here is y. The top of the box is therefore at y plus dy. And this ditto in z, the box is z, and z plus dz are the coordinates of the corners of this box. Let's work on the forces, and right now I'm only going to do the x forces, but these happen in the y and the z direction as well. So let's start where we're familiar. On the left-hand side of the box, there's a pressure, but to turn the pressure into a force, we need dy by dz. That's the area, right? So pressure times an area gives us the pressure force acting on the left-hand side of our box. And on the right-hand side, we have pressure as well. It's acting in the opposite direction. And it's the value of pressure plus, using the Taylor series expansions, which we went over in the continuity equation derivation, dp dx dx tells us the pressure evaluated at the right-hand side of the box, again multiplied by dA. So that gives us the pressure force. The other type of surface forces that are acting on this are the shear forces and the normal forces. And so in the x direction, there could be a shear force acting on the top of the box here and the bottom of the box there. We'd write this as tau yx. That's because it is the face that is normal to the y direction, and the force we're interested in is acting in the x direction. So tau on the y face in the x direction. Again, that's a shear stress, so to turn it into a force, we have to multiply it by its area, which the area at the bottom of the box here is dx by dz. There's a shear stress on the top of the box, again on the y face, because the y coordinate is normal to this face, in the x direction. So this is tau yx, but we're going to shift up using Taylor series again, so d tau yx dy. Again multiplying by the area to turn that into a force. We have that same idea happening on the front and back of the box. To keep things from getting cluttered, I've drawn it down here. So this now, we have this, remember this is the z direction, and so this is the z face. So we've got tau zx, and the area that it acts on is dx by dy. And then we're going to use a Taylor series to evaluate that value at the other side of the box, d by dz. And so there's that. Lastly, we have a normal force. This has to do with molecular bonds. And so there is actually a normal stress acting outwards on this box that we write as sigma xx. And that looks like it's acting on the area dy by dz. And then we're also going to evaluate that on the right-hand side of the box using a Taylor series again. Lastly, we still have to handle, we've just done all the surface forces. The last thing we have to handle are the body forces, such as gravity. Now remember, a little g here, remember F equals ma, all that kind of business, is a force over the mass. And so we're going to use that same kind of dimensionality for our body forces. So the body force is going to be this, which is force per mass. And then we have to multiply that by mass. Well, we know the mass of our system is the volume times the density. Okay, so we've got a lot of ingredients here. Let's look one more time. We want the rate of increase of momentum has to equal the sum of all these external forces and the flow rate going in and out. So let's move on to the next page and start looking at that. Hey, there we go. Okay, so right now let's just add up the forces. Adding up the forces, we had the body force in the x direction, plus we had the pressure acting on the left and the right-hand side. So we had it positive on the left, negative on the right. We use a Taylor series to evaluate them, multiplied by the area that they act on. We had the normal stress acting on the left and the right-hand side, and so we take the difference between those. Now they were pointing outward, so the left one was negative and the right one was positive. We had the shear stresses. Remember, those were on the bottom and top of the box. And so here's the delta between them. And then the ZX shear stresses, which are acting on the front and back of the box, and there they are taking their difference. Kind of like with the mass, the values themselves cancel out, plus P minus P, plus sigma XX minus sigma XX, and so on. And so what we're left with are just the derivatives. And conveniently, here's dx dy dz, this has dx dy dz, this has dx dy dz, dx dy dz. And so we can write all these derivatives and multiply them by the volume at the end. And don't forget the body force, which is here. I'm sure you could follow a similar pattern. This happens in the y and the z direction as well. Okay, but we need ma. So the mass of our cube, differential mass, looks like density times the differential volume. In this case, the volume was dx by dy by dz. Multiply that by density. And the acceleration, because we're dealing with fluids, is the substantial derivative. So that's the partial with respect to t. And then we've got this convective term out here, u du dx, v du dy, w du dz, that we learned about in kinematics. So if we sub all of that in, we've got mass, acceleration, and all the forces, and this beautiful thing happens where they all have dx dy dz multiplied on them, and so those cancel out, and we are left with, we are left with this for the x direction momentum. We have density times du dt, that's the rate of change of momentum in our system, plus all the convective terms, rho u du dx, rho v. All I've done is distribute this rho that came in. And then on the right hand side we have all the forces. And so you've got forces acting on your box, you've got momentum flowing in and out of the box, and you've got this extra term here for the transient effects. Now, with the Newtonian fluid assumptions, we actually have relationships for sigma and tau. And they look like this. So for example, tau yx looks like mu du dy. That's familiar, although there's always this cross term that actually shows up in real life. We've just been neglecting it thus far. And so if you take that and you sub it in, you get this weird thing, right? Because our equation has d by dy, where is it? Here we go, d by dy of tau yx. So we sub this in, this is a Newtonian fluid assumption, and take that derivative, and you end up getting this cross term, right? d by dy of du dy, well that's d squared u, dy squared. D by dy of dv dx looks like d squared v dx dy, and this is like this weird cross derivative. A really convenient thing happens if you do a math trick where all of these end up going away and you're just left with the straight terms and none of the cross terms here. And so finally, for a Newtonian fluid, the conservation of momentum in the x direction looks like this. All I've done is substitute in the Newtonian fluid assumptions. So on the right hand side, we have density times acceleration here. So this is like the ma side of things. You'll recognize this as just x direction acceleration from kinematics. And the other terms that we have are minus dp dx plus the body force plus all the stress terms that came from viscosity. And that's kind of the beauty of the Newtonian fluid, is these package up nicely. And what I want you to see is there's a certain parallelism to the different directions. So for example, if we were going in the z direction, we replace all the u's with w's, dp dz, rho g z, and our cross terms now, instead of having u in them, have w. And so we could do this for all three coordinate directions, but these are the equations that we call the Navier-Stokes equations when you add to them the conservation of mass for Newtonian fluid.